Greetings, here are some quick notes on blackbody radiation to accompany Chapter 1 of To Build a Star. So the Planck spectrum is the formal name for what's more commonly referred to as the blackbody spectrum. And this is the distribution of wavelengths of light that are emitted from an object that is essentially in thermal equilibrium with its environment. So the intensity is typically referred to using the variable B. And so, for a fixed temperature, your distribution is going to be a function B of lambda, right? So it's a function of the wavelength when you're at a fixed temperature. So given some temperature T, this is what defines your distribution. And it's an intensity, so the units are going to be watts per steradian per meter squared per nanometer. So when we actually plot the blackbody spectrum, it looks something like this. So for a fixed temperature, let's say we have a 3000 Kelvin object and it's a perfect blackbody, the distribution is going to look something like this for the intensity. Okay, now as you increase the temperature, you note that the distribution shifts to smaller wavelengths. It also gets more intense. And so this fact that the wavelength, the peak wavelength of the distribution is inversely proportional to the temperature. This is known as Wien's displacement law or Wien's law. So if you wanted to figure out where this peak wavelength was, what you need to do is find the maximum of this distribution. And you may recall that to find the maximum of a distribution, with respect to wavelength, you would take the derivative with respect to the wavelength. And when the derivative is equal to 0, that is an inflection point, and that's going to give you the maximum. When you do that, if you want to solve for when the derivative is equal to 0, keep in mind that the solution may not be analytic. You may have to solve this numerically or graphically. In this case, to be honest, I'm not sure that there is analytic solution. I only know how to do this one numerically or graphically. It's pretty much the same thing. So if you wanted to instead express the Planck spectrum in terms of frequency, you can just do the substitution that the speed of light is equal to the wavelength of the light times its frequency. So if we want to figure out what the outward flux is from a blackbody, then we would integrate over all of the outward angles. So you would integrate from 0 to 2 pi in the azimuthal coordinate, and in the angular coordinate you would just integrate from 0 to pi over 2, right? Because it's just half of the sphere that you're trying to encompass. So when you do that integral, which is in the book, then you see that the blackbody flux is proportional to the temperature of the object to the fourth. And you have all these constants here. You have Boltzmann's constant, Planck constant, the speed of light, pi, and some numbers. You combine all those together, and that gives you what's known as the Stefan-Boltzmann constant. So the flux of a blackbody is proportional to the temperature of that object to the fourth power. Okay, so the blackbody approximation is one that we're going to tend to use and move forward with. And the reason we do that is because it allows us to solve things analytically often. So in real life, stars are not quite black bodies, and you'll often see that astronomical objects are not black bodies. And it is something you should keep in mind in terms of doing research. But one thing you might wonder is, how far off really are you from the blackbody spectrum? Sometimes you can be pretty far off. So this is sort of a somewhat extreme example here for a star. You're looking at the flux versus as a function of wavelength. This is for an M-type star. It's a bit cooler in the atmosphere, and so that means you can have molecules in the atmosphere. And at the wavelengths corresponding to vibrational and molecular rotations, vibrations and rotational degrees of freedom of that molecule, you'll get these absorption lines. And so the overall shape is still pretty blackbody-like, but you get some severe deviations locally. Okay, so that's kind of an extreme bad case. You see the blackbody's still not too bad. It just isn't exact here. There are a handful of stars for which the blackbody approximation is really outstanding. So this neat paper from not too long ago, they looked at a huge sample of stars from the Sloan Digital Sky Survey, and they found a handful are just about perfect black body. So you can fit that with a black body, look at the residual from the fit, and you see that there's very little residual there. So basically the Blackbody approximation is what we're going to proceed with because it allows us to do things analytically. If you were actually doing research that required you to use a spectrum, you might initially use the Blackbody just because you understand it to get a feel for what the result would be, and then later you may incorporate a more realistic spectrum. So the Blackbody is a good starting point, and you can see here it doesn't do too bad. Okay, so from that Blackbody approximation, you saw that the flux from a blackbody is proportional to the temperature of that object to the fourth power. So if we just approximate our stars as a blackbody, which you saw isn't too bad, then we can derive the effective temperature of the surface of that object. So the effective temperature of the surface of the object is equal to the flux of the object divided by the Stefan-Boltzmann constant, and all of that to the fourth root, or to the 1/4 power. So you can plot then the effective temperature here on this Hertzsprung-Russell diagram where you plot the temperature versus the luminosity, and so you can read off basically the effective temperature here. So your peak wavelength will give you that. All right, so what does this mean if the effective temperature is proportional to the flux? And we know that the flux is the luminosity divided by 4 pi times the distance squared. You can ultimately relate the effective temperature directly to the luminosity of the object. So the luminosity is equal to 4 pi times the radius of your star squared times the Stefan-Boltzmann constant times the effective temperature to the fourth. So who cares? Well, what's interesting here is that you can actually then infer the radius of a star based on its position in your Hertzsprung-Russell diagram. Okay, so you can use the spectrum, fit the spectrum with a black body to get the effective temperature. You can measure the flux and the distance and use that to get the luminosity, and then plot that somewhere on your Hertzsprung-Russell diagram here. For instance, here's the sun. And then looking at this relationship between the luminosity, radius, and effective temperature, you can see that if you're at a fixed effective temperature, but a higher luminosity, that means that you have a larger radius object. Okay, so then as we go from increase in the vertical direction, at a fixed surface temperature, we're increasing the radius. All right, it's kind of interesting. And so you can see for giant stars and supergiants, which aren't too different in effective surface temperature from the sun, you can infer their radii just from the fact that they have a similar temperature and from their luminosity. So if we go to giant stars, you're at something like 100 times the luminosity of the sun. That means the radius of giant stars, of red giants, is about 10 times the radius of the sun. When you get to supergiants, just to make the math easy, let's round up a little bit to 1,000,000 times more luminous than the sun. These can get to about 1,000 times larger radius than the sun. And you know all of this just from this Blackbody approximation. Okay, so radiation pressure. So this is one of the components of pressure that props up your star against gravitational collapse. So you also have the pressure of an ideal gas. That's also a pressure propping up the star, but radiation pressure is one of the things that's obviously supporting that star against gravity collapsing inward. So how are we going to calculate that? Well, let's go back to intro physics that you know. So the pressure is just defined as a force divided by an area. Right? So that's physics 1. And again, from physics 1, you remember that the force, this is the rate of change of momentum. So dp dt. So our pressure is dp dt over area. All right. For a photon, or for any massless object that's relativistic, the momentum is equal to the energy divided by the speed of light. And now let's take a step back and recall that we know we've defined the intensity of the light. So the intensity, this is the amount of energy arriving within a given slice of time for light over a given slice of wavelength, coming in through a given solid angle, and going through a given projected area. So cos theta dA, that's a projected area, which just takes into account that your light may not be coming in perfectly perpendicular to your detector, for instance. So when you integrate this over all angles and all wavelengths, then what's going to happen is, your d lambda is going to go away, your d omega is going to go away, and what do you have? You have dE, dt, dA. Okay, change in energy over change in time over area slice. Well, because your momentum is just your energy over the speed of light, then dE over dt over dA, that's the same units here, right? So when we integrate over this intensity over all angles and all wavelengths, that gives you a force over an area, which gives you the radiation pressure. So the pressure from a single wavelength, you can again find this in the book. The pressure of a given wavelength is just directly proportional to your Blackbody spectrum at a given wavelength. So we have the pressure is just 4 pi over 3c times the Blackbody at one wavelength. And then obviously this is going to be for a fixed temperature as well. So then again, at our fixed temperature, if we integrate over all wavelengths, that gives us the total radiation pressure. So when you do this integral, you get that your total radiation pressure is 4 over 3c times the Stefan-Boltzmann constant times the temperature to the fourth. And people tend to wrap the 4 Stefan-Boltzmann constant over c into a constant just called A. And so then your total radiation pressure is 1/3 times AT to the fourth. All right, so one interesting thing to note here is that this is a really strong temperature dependence. Okay, so in a star, you're going to have different contributions to your pressure, and you can see that then for high temperature regions of a star, so for instance, the core of a high mass star, radiation pressure is going to become a very significant component of the pressure in that local environment because of this really strong temperature dependence. Okay, finally, we can consider the radiation density per wavelength. So the density of the energy, right, this is literally just energy divided by volume, and then per wavelength, that's energy density. And going back to our definition of intensity, you can see that the energy density per unit wavelength, we're just going to integrate this intensity over solid angle, so over 4 pi. So you integrate over 4 pi and you get this factor of 4 pi over c, right? And because the Blackbody spectrum doesn't depend on angle, it just pops out of the integral. So your radiation energy density per wavelength is 4 pi over c times the Blackbody spectrum at one wavelength, and of course at a fixed temperature. So then if we want the total radiation density, you can see that the total radiation density is just 3 times the radiation pressure, right? So this is our radiation pressure at a given wavelength, and this is the energy density at a given wavelength. If you integrate them over wavelength, you're still just integrating over the same Blackbody spectrum. So the only difference is this factor of 3. So the total radiation density is 3 times the total radiation pressure, and when you're relating energy density to pressure, that is an equation of state. So then you see this is the photon equation of state. And that is it for these quick notes on the Blackbody spectrum.